Hello. Is this working? Oh, hello. I'm very loud. Hi, guys. I was just saying earlier, this is my first time back in the States since like before 2020, so kind of nice to be back in more, shall we say, auspicious times. Today, I wanted to write something that is pretty near and dear to my heart and pretty near and dear to Cloudflare's data pipelines. I want to talk about Clickhouse. For the uninitiated few among us, they have a booth out there, but I swear they're not paying me to say this. But sounds good. Clickhouse is a Columnar DB at any rate. You can throw data at it, you can store it, you can query it, all that fun database stuff, but it does have one little trick up its sleeve. It's stupidly fast, like sillily, ridiculously fast, which makes it really good for analytical processing workloads. It's what powers the entirety of Cloudflare's analytics and most of our observability infrastructure at this point. As a columnar data store, it doesn't really care about the cardinality of your data so much. Data is stored group by column, and so whether you store 1 billion unique values or 2, Clickhouse doesn't care. In a world where big observability is pushing us towards larger events with more and more context and cardinalities, that's a great selling point. But this talk isn't just about Clickhouse, it's also about the golden child of the CNCF's observability offerings, Prometheus. Despite this big push into high cardinality data, Prometheus sort of remains steadfast in its inability to handle such data. One of the biggest things we have to do is, as an observability team, is chase teams down to get them to reduce their metrics cardinalities. And when they inevitably ask us why, our terrible answer has to be, well, our TSDB doesn't like it. To quote just about every overfunded tech startup bro ever, there's got to be a better way. What if we can take Prometheus's ecosystem, its scraping, its query abilities, its recording rules, its alerting rules, and augment that with Clickhouse's high cardinality abilities? So we get all of the familiarity of things like PromQL, but without any of the awkward things like our metrics database ooming every time someone looks at it. Weird. Well, turns out we can. But before we get into that, hi, I'm Colin Douch. I tech lead our observability team at Cloudflare. We build, maintain, and operate all the tooling that helps Cloudflare debug Cloudflare. And part of that is operating a pretty sprawling network of Prometheus servers these days. Cloudflare operates some of, if not the largest ClickHouse clusters in the world. So this felt like something pretty natural to try out. I guess the first question before we start is, how can we do this? I assume most people here who are vaguely familiar with the Prometheus ecosystem have heard of remote write. Yeah. For the uninitiated, remote write is a mode of Prometheus that allows us to use Prometheus's scraping abilities to gather data, but then ship that data off to something else over the network. Crucially, that doesn't have to be Prometheus. It can be Cortex or Mimir or Thanos Receive or, hell, your neighbor Henry down the road, so long as he speaks remote write and doesn't mind, which is pretty neat, right? We can take that scraping ability and then put it into whatever we want behind a remote write bridge. Maybe we can put it in Clickhouse. Yeah, turns out you can, actually. There's a code link there, but Prometheus provides protobufs for these things, so it's pretty trivial to write something that takes a remote write request, translates it into a Clickhouse insert statement, inserts it into Clickhouse. To get data out, we do have to do the other side, rather boringly, I think, called remote read. But it's the same thing. Prometheus provides protobufs for these things. We can write something that takes remote read requests, translates those into SQL select statements, packages the whole data back up into a remote read response, and ships that back. Kind of neat, right? We can pretty trivially get data in and out. We've done a bunch of experiments. How does it fare, right? Let's have a look. Before we get too much into it, we're trying to be good scientists. So, let's talk about sort of setup, testing setup quickly. In terms of hardware, a standard Cloudflare compute node is a 92-core, 1.92 gigahertz CPU, 2.4 terabytes of NVMe SSD, technically 1.2 terabytes in a RAID, but and 256 gig of RAM. For some time series data, we've grabbed about 24 hours worth of real data from one of Cloudflare's Prometheus servers. 24 hours may not seem like a lot, but it's still about 850 gig of data, plenty enough to form some representative numbers. We could have used some existing benchmarks here. Victoria Metrics does have a good one, but I figure we've got production data, we might as well use it. The problem there is that these are completed blocks. They're not something we can remote write, really, but again, we can use Thanos' libraries this time to translate those completed blocks back into something that we can remote write. We do lose some information. Prometheus rather sneakily doesn't actually do things like store the type or the help of your time series, but we get enough that we can reconstitute it back into a remote write request. Again, code link there if you want to have a go with your own data. For queries, we grabbed out a week's worth of queries from that same Prometheus server. It may come as a surprise. Most people aren't dweebs like me. They aren't constantly querying Prometheus. And so we need to look a bit further than that 24 hours worth of data to get something vaguely representative for queries. So we look at 7 days. It does run into a bit of a problem where that set of queries may no longer be relevant for the data we have. So we can run a bit of a quick post-processing step, throw out anything that doesn't match any data. Who needs it, right? Not us. For a bit more of a nuanced comparison, we can split those up into 3 buckets, which we'll call small, medium, and large queries. Here's a breakdown of how many fit into each one. Small queries are going to be 1 time series queries. It's hard to say. Medium queries are going to be like 2 to 3 time series, and large queries are going to be more than that. For a bit of demonstrative, small queries tend to be like error rates, request rates. Medium queries tend to be ratios, one value over another, or one value over a sum. Large queries tend to be large ad hoc things, like this thing that I imagine our network team managed to summon through some sort of extra planar entity. I really don't know, but it's simultaneously the most impressive and disgusting thing I've ever seen on our Prometheus servers. And it takes a whole 30 seconds to run. So, maybe something interesting for benchmarking. So with our replay tool, we can reconstitute a remote write request. We can replay it against our Clickhouse server through our Prometheus bridge. We can run queries against it. We can pull numbers. Let's see. Clickhouse is a structured database to begin with, so we do have to define a schema up front, but we can be pretty generic with it and start with something kind of trivial and pretty similar to what Prometheus does, to be honest. We'll start with a double delta encoded timestamp. We'll split the name out into its own field. We'll have the rest of the labels in a map, and we'll have a double delta encoded value. Again, pretty similar to what Prometheus actually does. Let's push some data in, shall we? Here's disk usage. You see we go up and up and up. That orange line is what Prometheus is storing. We go up, we go up. We cap out around 1.8 terabytes, which, at double and a half what Prometheus is storing is not a great start, to be honest. But something kind of weird happens if we just let it sit for a bit. Our disk usage actually starts to go back down, which is real weird, right? We're not deleting data. So what's happening there? This is one of Clickhouse's kind of magic tricks. I sort of skipped over it here. We have this engine equals merge tree bit. That's not normal SQL. Clickhouse defines a bunch of table engines, which sort of define how your table functions in the background. One of the merge tree's big tricks is that for every batch of data that is pushed, it forms what's called a part. Parts, crucially, are independent. They don't need to be coordinated in any way. So ingestion becomes real fast. We don't need to do any sort of locking or anything. But we do end up with these individual chunks of data, and compression and all of the other nice features apply over those individual parts. Where the merge tree comes in is that it merges those parts together, perhaps, obviously. And because compression applies over a part, and because we have so much duplication in our label names and our label values, our compression ratio skyrockets, and as we merge parts, our disk usage starts to go back down. It's kind of neat. We cap out around 1 terabyte. Still not as good as Prometheus, but I mean, better than it was. Let's look at query times. Like, it's all well and good to want to get data in. We probably want to get data out, right? As a hypothesis, we can probably assume that Clickhouse might be slightly slower than Prometheus, mainly because Prometheus cheats a bit. Most of our queries are instant queries for the latest data, right? Like, that's what you want to alert on. Prometheus cheats by storing this in memory in its head chunk. Clickhouse doesn't have that luxury. It can do some level of caching, but there's no real way to say, let's store only this latest data in memory. So we can maybe assume that Prometheus is going to be a bit better. Remember, we've got our 3 types of queries. There's median times for Prometheus. Here's a breakdown of how Clickhouse performs against Prometheus. Again, our query times are slightly above what Prometheus is doing, as we assumed, but not terrible. We can work on it. Large query times are a bit more ridiculous and represent exactly why I've split these out. For the most part, all of the large query graphs look like this. They're all these giant long tails of stupid queries people are running, and they do nothing except compress the graph and make it hard to read. I will include these if they're interesting, but I'll leave them for the rest of it. But even though we're lagging behind a bit, it's kind of neat that we're able to get semi-close with a naive schema on an unstructured, well, a non-specific database. Let's talk about low cardinality fields, though. Might be a bit confused, because I started out this talk saying, let's talk about high cardinality. Low cardinality to Prometheus and low cardinality to Clickhouse are 2 very vastly different things. In Prometheus, we try and keep cardinalities to like 10s to 100s, maybe, because of that annoying combinatoric explosion problem where your cardinalities sort of multiply together. Clickhouse docs recommend low cardinality fields for columns with up to 1 million unique values, so like different ballparks entirely. Under the hood, Clickhouse's low cardinality field forms what's called a dictionary encoding. At the moment in our naive schema, we're storing names and labels as basically literals in each sample, tremendously inefficient. In low cardinality fields, we instead split those literals out into sort of a mapping, and we store those literal values next to a mapping value, and then we store that mapping value rather than the literals. Right? That should compress a bit better, maybe. Let's change up our schema a bit. We can slap low cardinalities around our strings, do the same tests. We go up, we go down. A bit disappointing, to be honest. We cap out slightly worse than just storing values literally. I feel lied to. Our Clickhouse team told me this would work. It didn't. I was very sad. We actually do slightly worse. We're about like 20, 30 gigabytes larger, which kind of sucks. Query times are not that much better. We do get slightly higher query times, but we do shorten our tails. It seems, profiling it, that most of those come from the reduced disk I/O from having to load data, because we're only having to sort of deserialize our label values and label names once per part. Not that great, though. Let's talk about nested fields. Nested fields are another way of storing KVs in Clickhouse. We currently store maps, but what we can do is instead split our labels into a nested field containing a key and a value. This might be a bit confusing. It's basically the same as a map, right? We're still storing KVs. The difference here comes from how Clickhouse lays it out on disk. In a map, there's like 8 different hash maps in Clickhouse, by the way, but generally, Clickhouse stores a map as a hash map, like values next to labels. or values next to names even. Whereas in a nested field, instead of storing everything next to each other, we're instead storing two separate arrays, one of names, one of values. The logic here is that if we take just our label names, we have a lot more duplication than if we take names and values together. So maybe it should compress well. The downside is that we're potentially nuking our query times because this turns an ON or an O1 lookup in a map into an ON lookup because we're having to linearly scan the name array to find an index into the values array in order to match against. But our ends here are like 10, right? We only have maybe 10 to 20 labels at most. Maybe it won't be so bad. We go up, we go down, same pattern, but this time we cap out around 380 gig. This graph, more than anything else, kind of surprised me. We're storing like half of what Prometheus is storing, which is kind of ridiculous, right? We go up, we go down, we follow that same pattern, and it's very confusing how it's able to do that. But again, we're getting pretty cool compression rates. Query times kind of suck, though. Remember how I said it might be okay? Turns out it's not. When you're linearly iterating over billions of samples, turns out that ON kind of kills you. We're doing like 4 times what Prometheus was doing, which, I mean, we're talking about hundreds of milliseconds, maybe seconds here. Are people going to care about getting a couple of seconds latency on their query? Maybe not, but this still kind of sucks. Weirdly, it doesn't affect the long tail of queries that much. We still get around 43 seconds or so. It seems like most of this comes from regex matching at this point, rather than actually finding values to match against. Let's talk about Prometheus encodings. Who here knows how Prometheus encodes data, like on disk? I see a few hands. That's good. I see some cheaters as well. Rather opaquely, Prometheus has 3 types of encoding called type 0, type 1, and type 2. Quick refresher, type 0 is delta encoding. Basically, if we have the values 0, 5, 12, instead of storing 0, 5, 12, we store 0, our initial value, we store 5, the increase, 7, the increase. Delta encoding, type 0, basically never used, so treat me as if I was just an adult from Peanuts there. Ignore it completely. Type 1 is double delta encoding. Instead of storing 0, 5, 12, we store 0, our initial value, 5, our initial delta, and then 2, our increase. This is what Prometheus uses by default. This is what we're using. The advantage of this is that if we have linear values that are increasing linearly, like a timestamp that increases every 5 seconds, this compresses down to 0, and zeros compress really well. Type 2 encoding is where things get fancy. Type 2 encoding is based off of Facebook's Gorilla encoding. There are entire papers and entire talks about this. I'm not going to go into it, but the trade-offs are kind of nice to talk about. There's 2 real things to consider. Gorilla is a variable length encoding, which means that values have different numbers of bits. Facebook claims they get down to like 11 bits per sample, which when we're ostensibly storing 64-bit floats is kind of impressive. The downside is that we can't sort of jump into the middle of it with an index like we can with an array. We have to iterate from the beginning of a set of samples in order to find the offset. So the trade-offs here are better storage space, but potentially slower query times. Clickhouse supports Gorilla encoding. Let's see whether those are true. Disk usage, we go up, we go down, we get pretty much the same thing. We save about 30 gig or so, 10%. It's not bad, it's not great. Gorilla encoding, kind of disappointing, to be honest. It makes sense, though. It seems like most of our storage space at the moment is coming from like our labels rather than our values. Optimizing values doesn't seem to help us that much. Same trade-off here, we seem to get slightly higher query times. Gorilla while fancy, doesn't seem like it's worth it, to be honest. It makes sense that Prometheus's default is double delta. Let's change tack for a bit though. We've optimized our query time, we've optimized our disk usage kind of nicely, right? We're storing just over half of what Prometheus is storing. Kind of neat, but at the same time, we've tanked our query times. We're doing like 4 times what Prometheus is doing. Let's see whether we can remedy that. It's probably worth looking at what exactly is slow here. We can sort of see 3 real patterns. If we take our like P99 slowest queries, they all contain lots of regex matches, but kind of interestingly, we're not doing anything that is particularly regexy. They all form like one of these 3. I think this covers like 98.7% of our query corpus when I ran the numbers. We either have lots of values ored together, we have prefix matches, or we have substring matches. Interestingly, Prometheus actually has optimizations for these. They can scan those list of ors and split them out into exact matches with inverted indexes and things like that, which is kind of annoying because it would be nice if PromQL could better express this and we didn't have to pass regexes. Victoria Metrics' MetricsQL actually has explicit ors for this purpose. That would be nice. But again, we're not crucially doing anything particularly regexy. I sort of glanced over it, but in our bridge, we're translating those regex matches into Clickhouse match statements, which is incredibly inefficient, as the docs warn us. But we can sort of split those 3 out into more native queries, right? We can split out our ors into or statements. We can split out our prefix matches into starts with statements. We can split out our substring matches into like statements. The rest of that 1.3% has to fall down into matches, but maybe we can speed things up. With these optimizations, we do far better. We're doing a vast improvement over that more naive sort of match while retaining our disk space improvement, which is kind of nice. We might be able to do better though. The remaining long tail on that are those substring matches. I sort of skipped over it again. A primary key in Clickhouse here is how it's going to sort values in those parts. And we're sorting by name and then labels and then timestamp. This is what groups individual samples in a time series together, which is what allows us to get those huge compression ratios. This works really well if you want to do exact matches or prefix matches because things are stored sorted. For substring matches, it still becomes a linear search. What we can try is some indexing. This is a very scary name. Ngram BFV1 is incredibly opaque in terms of what it is. We can break it down a bit. An ngram index is effectively a sliding window of a given size, n. So we can move a sliding window of, say, 5 characters across our string, which breaks it up into ngrams. BF there is a Bloom filter, basically a set. So we can jump really quickly to samples that have a given ngram with this index. Those big long string of numbers, very opaque. You don't need to care about any of them. The only one that's slightly interesting is that first one. That's the n of our ngram. 5 we've chosen entirely empirically. Most of our substring matches seem to be a size 5 because they're over Cloudflare instance IDs, and our instance IDs are 5 or 6 sort of character long names. That could do with some tuning, but let's see how it goes. Disk usage, again, we go up, we go down. We cap out around 480 gigs. So we're storing extra 100 gig for our index. Not terrible, and we're still way below what Prometheus is storing. Our query times are kind of exciting, though. We've dropped down a little bit, but we've still been able to get pretty close to Clickhouse. Again, we do get those longer tails, but that mostly seems to fall down to disk I/O and cache misses. There's not much we can start to do there, but my time is running out, so I thought I'd leave it there with a bit of a final comparison of what we've been able to achieve. You can see Prometheus is storing on disk about 750 gig or so. Clickhouse was storing sort of down about 380, extra 100 if we introduce that index because of how we've used Z standard and how we've laid out our columns. In terms of queries, we're still not quite there. I'm not sure we're going to be able to get over that heap of Prometheus cheating, but we get close enough. And I mean, it's still pretty impressive as a non-specialized DB. Before I go, there's so many more experiments we want to do here. We're not even touching on things like Clickhouses, sort of horizontal scaling abilities with replicated merge trees. We're only storing one table, and so we could split it out and do our own deduplication there. We can tune our indexes. We can look at things like Snappy rather than Z standard. Again, so many more things to consider. You might see me back talking about more things. Again, we love Clickhouse at Cloudflare. So that's about me. Thanks. I do wonder, as an observability sort of world, are we going to see an increase in observability startups using Clickhouse? Like all of those first wave observability startups founded on their own databases, are they going to see more competition from these new startups that have a DB ready to go? It'd be interesting.
Awesome, great work. We've got time for a couple questions. Any questions from the audience here? We got one right down here.
Yeah, so you had mentioned that one of the appealing things about Clickhouse was its ability to handle high cardinality. Did you do any head-to-head query performance testing against Prometheus using specifically very high cardinality data? And if so, did you see a big improvement there?
Did you do any testing of high cardinality data between Prometheus and Clickhouse?
The fun thing about Prometheus is that if you try to do high cardinality data, it ooms. And so there's not really many comparisons you can draw there beyond it works in Clickhouse.
Yeah, next question.
What about comparing to a product derived from Clickhouse, like Victoria metrics?
Yeah, what about products derived from Clickhouse?
That is a good question. Victoria Metrics actually steals a lot of ideas from Clickhouse in terms of its storage APIs. We have benchmarked Victoria Metrics a lot at Cloudflare. We do find that there are a lot more micro optimizations in Clickhouse that do help, but it does get a lot closer than what Prometheus does. The only reason we aren't using Victoria Metrics at Cloudflare is that switching would lose us a lot of operational expertise more than anything. That's the harder part. Like, technically, it is a better product, in my opinion.
I think we have time for one more question. Is there anyone at the top? One at the top.
What was the highest cardinality vector?
What's the highest cardinality vector? Number? Yeah.
That is a good question. The fun thing about doing this sort of thing is that it does enable us to just throw in arbitrary cardinalities. We split out individual metrics for like all of our premium enterprise customers. So we have like tens of thousands there. We also have instances like per interface on our switches, and we have hundreds of thousands there that we measure all sorts of stuff on.
All right, let's give a round of applause for Colin.